I welcome you all to the session of engine system and performance, and in today's class we shall discuss about an important map that is known as performance map, which is used to compare the performance of two dissimilar SI engines, and afterward we will solve, or rather we shall derive some analytical expressions which are used to predict the performance of SI engines under varied ambient conditions. So, if we recall what we could discuss in the last class are the air consumption of SI engines, then performance curves of SI engines, then engine characteristics of SI engine. That means, we had tried to map, or we had tried to see the variation of engine power output with engine speed keeping load constant, then again with different engine loads keeping speed constant. What we could not discuss is the performance comparison of two dissimilar engines. That means, if the engines are having different cylinder, different sizes and different shapes as well. So, it is very important to have one particular curve or map which can be used to compare the performance of two dissimilar engines. Now, the question is, as I said repeatedly, the performance curves we have seen, we have discussed in the last class are not suitable to compare the performance of one engine with that of another engine of different size. So, if we need to have a particular map which can be used to compare the performance of two dissimilar engines, that means engines of different cylinder sizes and shapes, then we need to have some performance data, a presentation of performance data on the basis of generalized parameters like BSFC, that is brake specific fuel consumption, brake mean effective pressure, that is BMEP, and mean piston speed, because these parameters are basically used to represent the performance of engines having different sizes. Rather, this data, that is these parameters, right, that is BSFC, BMEP and means piston speed, all these parameters are independent of reasonably engine cylinder, or that is cylinder shapes and sizes. So, if we go to see the map which is used to compare the performance of two dissimilar or dissimilar engines, the map looks like this. What we can see from this particular map is that the along the x axis engine speed is described. It can be mean piston speed as well. So, if I write here, that is speed, and along y axis output, that is brake mean effective pressure, this particular parameter is described. So, this is BMEP, and in this curve we also have mean piston speed. I mean, as I said, along x axis in the bottom we have engine speed, along x axis at the top we have mean piston speed. So, what we can see, essentially this map shows the contour or contours of constant BSFC, right. So, all these are BSFC. Now, as I said you that we wanted to have presentation or representation of performance data on the basis of some generalized parameters. Those are brake mean effective pressure, BSFC, which are shown in this map by these contours, and mean piston speed. So, in this figure or in this map which is known as performance map, we can see these contours. So, rather this map shows the contours of constant BSFC. So, if I write here for the sake of completeness, then this map plots the contours of constant BSFC in the load speed plane. Okay, because break mean effective pressure is essentially the representation of load. Now, this particular curve or this particular map is obtained by performing test on a SI engine having cylinder volume 2 decimeter cube. So, if I write here, this is 1. So, this map plots data set comma obtained from experiments conducted on SI engine having cylinder volume 2 decimeter cube. So, that is important to know. So, basically now question is, if we try to have another performance map of another SI engine, the qualitative rather the map should be similar both qualitatively as well as quantitatively if we maintain almost that cylinder volume same. So, essentially what we can tell from this particular map is, this map is very useful to compare the performance of two different engines, that is engines of different cylinder sizes. So, as I said you that this is in experimental data obtained on SI engine having 2 decimeter cube and 4 cylinders. Okay. Now, this is very important. What we can see from this map, and all these contours are basically contours of constant BSFC. And if we look at this map carefully, we can see there exists a region of a single valued minimum BSFC region. So, if we look at this map, we can see clearly this map. If I just try to mark, this map is having, or there exists a region of single valued minimum BSFC region or single valued minimum BSFC island, which is also known as. So, this particular region is known as single valued minimum BSFC island. Now, this is having, rather this particular contour corresponds to BSFC 275. So, this BSFC is 275, it is not very it is not seen clearly from the contour plot, but this particular BSFC contour or the contour corresponds to BSFC 275 gram per kilowatt hour. So, this if I write the single valued minimum BSFC island is there in the performance map and this single valued BSFC island corresponds to constant BSFC contours of 275 gram per kilowatt hour. Okay. Now, I would like to discuss a few salient points of this particular map, and these salient points are as follows. So, starting at this minimum BSFC island, we can see BSFC or fuel consumption rate increases in all other directions, because all other contours are having BSFC value which is higher than 275. That means, starting at this minimum BSFC contour or minimum BSFC region, in all other directions mass flow rate or for fuel increases. So, another two important salient points are, if one would like to traverse towards right from this minimum BSFC island at a constant load. So, this particular region corresponds to minimum engine speed and moderate to high engine load. So, if I take these these two lines, and if we take projection of this line on this x axis, then we can see this particular island corresponds to engine speed which is not very high, while this particular regime corresponds to engine load which is moderately high. Now, if someone would like to traverse from this particular regime towards right for a constant load, then again fuel consumption rate increases, and that is attributed to frictional effect, because if engine speed increases, frictional loss will increase, frictional loss will be more, and which in turn will necessitate higher fuel consumption. On the other hand, at a constant load, if we reduce engine speed, that means if someone would like to traverse from this point towards left, then again we can see fuel consumption rate increases, and that we have discussed, because at low engine speed, engine cylinder will get sufficient time to transfer heat to the coolant or to the ambience, and sufficient heat transfer rate will again necessitate or will demand higher fuel consumption. The last or the final salient point that I would like to discuss is, instead of that constant load, someone would like to traverse at a constant speed. So, if someone would like to keep the speed constant and traverse towards upper side of this map, that means if load increases, fuel consumption rate will increase. That is quite obvious, because we need to enrich the charge, that is we need to supply more amount of fuel. But if someone would like to traverse towards bottom part of this map, that is keeping speed constant, if load decreases, then again we can see fuel consumption is becoming more, and that is that when load is less, a significant part of this is used to overcome the frictional losses, and that is why fuel consumption increases. One particular point I should mention before I go to discuss about the analytical method of engine performance. Now, or analytical expression which we shall drive in today's class, the upper part of this map is essentially the corresponds to full load operating characteristics, while the lower part of this curve corresponds to part load operating characteristics. So, with this we can say that this particular map is really very useful and suitable to compare the performance of two engines having different cylinder sizes and shapes. Okay. Next we shall discuss about analytical method, or we shall try to have some expressions analytically, and those expressions can be used to compare or predict the performance of engines under different operating conditions. So, let us start our discussion on this particular part, that is analytical method of performance estimation. So, if I write here analytical method of performance estimation. So, that is important. Say it is not possible to perform tests if the operating condition changes. So, if we have a particular engine and if we know the performance characteristics of that engine at a short or at a given operating condition, then using these analytical expressions we can easily predict the performance of that particular engine when operating condition will be changed or different operating condition. So, let us start with that we shall consider. So, we will consider a 4-stroke cycle naturally aspirated. Engine. So, what is naturally aspirated engine? Because by this time for this particular engine there is no need of supercharger or turbocharger. That means intake air will be drawn into the engine cylinder only due to the atmospheric only due to the pressure difference, that is the atmospheric pressure minus cylinder pressure. So, there is no supercharging unit to push or to drive air into the engine cylinder. So, that is called naturally aspirated engines. Naturally aspirated engines have a few advantages, like it is cheap, then reliable, easy to maintain, but disadvantage is low power to work ratio, weight ratio. So, there are many advantages, as I said very cheap, easy to maintain and reliable, while disadvantage is low power to weight ratio. So, now question is, if we consider 4-stroke cycle naturally aspirated engine and if we try to have or try to derive the expression which can be used to predict the performance of engine or engines under varied operating conditions, and essentially we are trying to derive all these expressions analytically. So, to start with that let us write. So, what is, we know that when we try to extract power output from engine and we get such power output at the cost of some input energy, and that input energy is essentially the energy which is being supplied to the engine with the fuel. So, if we consider that supplied energy to the engine is Q into MF, mass flow rate of fuel. Okay. So, this Q CV, so this is the calorific value of fuel, calorific value of fuel and mass flow rate of fuel. Okay. So, basically this is the energy that we are supplying to the engine. Now, we can write this expression again. So, this is equal to we can write QCV. So, this is F into m dot A, where F is the fuel air ratio. So, that is fuel air ratio. So, that is nothing but m dot F by m dot A. So, m dot F is equal to F into m dot A. Okay. So, if you go to the next slide, so knowing this is basically this m dot A is the mass of air per cylinder per cycle. So, this is mass flow rate of air per cylinder per cycle. So, if you go to the next slide, then you can write this m dot A, we know that is mass per cylinder per cycle can be determined if we know the volumetric efficiency into cylinder volume into inlet air density. So, that is the actual, this is the theoretical mass flow rate of air that we have discussed in the previous, in our previous class. So, that is the cylinder volume or stroke volume also, that is m dot A. So, what we can do from here now, and this rho I is the density of air, incoming air. Okay. So, now what we can do, we can write that. So, basically this is the volumetric efficiency. So, we can write the indicated work done So, we know the energy supplied to the engine, and if we try to have indicated work done, so indicated work done by this energy supplied to the engine is equal to indicated thermal efficiency. So, indicated work done is equal to indicated thermal efficiency I, that is that or I should write, because we have to use this term several times. So, indicated into, this is indicated thermal efficiency into, so heat released or heat or energy supplied to the engine, not transferred, energy supplied to the engine, right. To the engine, that is nothing but eta indicated into heat supplied to the engine. If we go back to the previous slide, then we can write that equal to Q Cv into F into m dot A, while m dot A equal to this. So, then if we plug in the value, that is Q Cv into F into m dot A, while m dot A is equal to eta V into stroke volume into rho I, that is what we can write. Okay. So, this term is the indicated thermal efficiency. So, if we go to the next slide, so it is very clear, essentially this quantity is m dot, this quantity is F into m dot A, m dot A into F. Okay. So, if we go to the next slide, then we can write. So, once we have the indicated work, that is work available inside the cylinder, from there we can easily write some mathematical expression of indicated mean effective pressure from the work done. So, PdV, that is indicated work done, is essentially PdV. So, indicated mean effective pressure is continuously changing inside the engine cylinder. That is why the concept of mean effective pressure was introduced. So, if we know the indicated work done, we can have some estimate of indicated mean effective pressure. So, if we go to the next slide, then we can write indicated mean effective pressure. So, this quantity is indicated mean effective pressure into stroke volume. So, this is stroke volume. So, or cylinder volume I should write. So, here it is also stroke volume. Or, so if we now go to this, so this is essentially the indicated work done that we have already derived here. So, this is indicated work done, that is eta indicated into this. So, this quantity is nothing but indicated mean effective pressure into cylinder volume or stroke volume. So, if we go to the next slide, then we can write this equal to QCV into F into rho I into Vs into eta volumetric efficiency into eta indicated thermal efficiency. So, from here we can write one expression, that is indicated mean effective pressure equal to, we can write QCV into F into rho I into eta V into eta indicated. This means indicated mean effective pressure is proportional to F into rho I into eta volumetric into eta indicated. So, this is very important relation that we have. Using this relation we can have the information about indicated mean effective pressure under two different conditions. So, if we try to write that, so for two different or two operating conditions, this is we are giving name of equation 1, this is equation number 1. So, using this expression we can have for two different operating conditions or two operating conditions, we can write using this equation 1 that I mean effective pressure 1 divided by I mean effective, or I can write 2, then I mean effective pressure 1 equal to, so this is 2. So, equal to, I can write F2 into rho 2 into eta V2 into eta indicated 2 divided by F1 into rho 1 into eta V1 into eta indicated 1, right. So, say this is equal to Ri, say. So, this is equation number 2, right. Here 1 comma 2, this 2 denote 2 operating conditions. Okay. So, having analytical expression of indicated mean effective pressure, we can now try to have brake mean effective pressure, or then we can have brake horsepower. So, we can write that brake horsepower BHP that equal to, we can write brake mean effective pressure into volume into N by 2, right, forced cylinder. So, 4 stroke cycle engine. So, there are 2 revolution per cycle. So, N by 2, from there we can write this is the brake horsepower. So, brake mean effective pressure into, so PdV work. So, this is brake mean effective pressure into Vs, that is brake mean, so that is brake work, multiplied with this we can have power, that is brake horsepower. So, now that means we can write BHP is proportional to brake mean effective pressure into N, that is speed of the engine. Okay. Now, what we can do, again we can have this expression for two operating conditions, that is 1 and 2. So, if we write 1 and 2, so between two states, right, 1 and 2, we can write 1 comma 2, we can write BHP 2 divided by BHP 1 equal to brake mean effective pressure 2 divided by break mean effective pressure 1 into N2 by N1. That is what we can write. So, this is equation number 3. So, if we box again, if we keep this under or inside the box, then it is equation number 3. Okay. So, the question is, say if the speed is, assume the speed is remaining same. So, N1 equal to N2. So, if I write here, say speed is constant, that means N1 equal to N2 equal to N. Then what we can write? We know that brake power equal to indicated power minus frictional power, that we know. So, indicated power is not available, this power is available inside the engine cylinder, while the power available at the shaft is brake power, which is indicated power minus the friction power. So, this if we write, then we can write brake mean effective pressure equal to indicated mean effective pressure minus frictional mean effective pressure, that you have studied in your undergraduate internal combustion engine course. So, that means what you can write now, that here we have brake mean effective pressure at state 2 divided by brake mean effective pressure at state 1. Can we write this in terms of indicated mean effective pressure and frictional mean effective pressure, while frictional mean effective pressure be the same for the same speed, but indicated mean effective pressure between these two states already we have some expression. So, now what we can write is, we can write this brake mean. So, we can write brake mean effective pressure at state 2 by brake mean effective pressure at state 1, that equal to indicated mean effective pressure at 2 minus frictional mean effective pressure at 2 divided by indicated mean effective pressure at 1 minus frictional mean effective pressure at 1. We can write one step further, that means if we divide both term by indicated mean effective pressure 1, then I can write that is IMEP 2 divided by IMEP 1 minus FMEP 2 divided by IMEP 1 divided by 1 minus FMEP 1 divided by IMEP 1, right. So, this is the expression. Now, as I said that if the speed is constant, so for a constant speed, that is N1 equal to N2 equal to N, this F mean effective 2 equal to F M E effective 1 equal to F mean effective pressure. Okay. So, with this we can further write this expression here, that BMEP state 2 by BMEP at state 1 equal to IMEP 2 divided by IMEP 1 divided by minus FMEP minus IMEP 1. So, that is very important, divided by this is 1 minus FMEP divided by IMEP 1. Now, we already know, if we go back to the previous slide, wherein we have written IMEP 2 divided by IMEP 1, that is Ri. So, we can write here that this is equal to Ri minus FMEP divided by IMEP 1 whole by 1 minus whole divided by 1 minus FMEP by IMEP 1. So, this is equation number 3. So, this if I keep inside this box, then it is equation number 3. This is equation number 4 rather, because already we have equation 3. So, this is equation number 4. So, this is equation number 4. As I said you that we are trying to derive some expressions analytically, and these expressions can be used to measure the performance of engine under 2 operating conditions. It is not really possible to perform test for each condition. So, performing test on engine at a given condition, we can use these expressions to predict the performance at or under different conditions. So, this is what we have written. So, now question is, we have this we have relations between 2 operating conditions in terms of indicated mean effective pressure, brake mean effective pressure. If we try to recall, today in the beginning we have discussed that if we need to compare the performance of 2 dissimilar engines, it is convenient to represent performance data in terms of generalized parameter like BSFC, BMAP, etc. So, now let us consider what is BSFC. So, if we try to have relationship between the 2 states 1 and 2 in terms of respective BSFCs, then we can write that we know BSFC divided by ISFC is nothing but IHP divided by BHP, okay, equal to I mean effective pressure divided by brake mean effective pressure. So, which is again nothing but indicated mean effective pressure by indicated mean effective pressure minus frictional mean effective pressure. So, we could write this that BSFC by ISFC. Try to understand, BSFC is m dot f divided by per unit power developed. Similarly, ISFC equal to m dot f by IHP. So, now if I write BSFC by ISFC, m dot f will get cancelled and essentially will be having IHP by BHP, and IHP is nothing but IMEP into, so this is the pressure into stroke volume into n by 2. This is also brake mean effective pressure into stroke volume into n by 2. So, stroke volume into n by 2 is common in both numerator and denominator, and so essentially we will be having IMEP, and this BMEP is written in terms of indicated mean effective pressure minus frictional mean effective pressure. So, if we consider this relation for 2 conditions, state 1 and state 2, we can write now that BSFC 2 divided by ISFC 2 equal to I mean effective pressure 2 divided by I mean indicated mean effective pressure 2 minus frictional mean effective pressure 2, and we can write BSFC 1 by ISFC 1 equal to I mean effective pressure 1 divided by I mean effective pressure 1 minus FMEP 1. So, this is what we can write based on the expression or based on the above expression. And okay. So, if we divide one by other, then we can obtain. So, if we go to the next slide, so that is dividing one by the other, we can write or we obtain, just I am writing here BSFC 2 divided by BSFC 1 equal to ISFC 2 divided by ISFC 1 into 1 minus FMEP 1 divided by I mean effective pressure 1 divided by 1 minus 1 upon Ri, that is nothing but indicated mean effective pressure 2 divided by indicated mean effective pressure 1, that already you have defined in equation 1, into FMEP 2 divided by IMEP 2. So, this is equation number 5. So, this is equation number 5. So, essentially what we did, we had tried to establish the expression of indicated mean effective pressure, break mean effective pressure, and finally indicated horsepower, brake horsepower, and finally brake specific fuel consumption. We have tried to relate BSFC with ISFC. Now, this is what we have done, all these the derivation of all these expressions analytically. Now, question is, next we will consider the effect of ambient conditions, if the ambient conditions change on the performance of 4-stroke cycle naturally aspirated engine. So, it will not take much time. So, now let us consider effect of ambient conditions on the performance on the performance of a four-stroke cycle naturally aspirated SI engine or naturally aspirated engine. We did not specify whether it is SI engine or CI engine, because these expressions are valid for both SI and CI engines, but it is valid for naturally aspirated engine. So, the engine is not using any supercharging unit. Okay. So, what we can do, for it will we have to first understand. To this, first we can write that Pi and Ti. So, subscript I denote inlet condition. So, subscript I here denote inlet conditions. So, these are the inlet pressure and temperature, right. So, question is, let us assume that inlet mixture, which is not this is a mixture of dry air, wet air, also the fuel vapor, right. So, if it is a SI engine, certainly this would be mixed with the fuel vapor. So, even for the modern CI engines, fuel is sprayed into the intake manifold. So, what we can write, this Pi, that is the pressure of the mixture, using assuming that the component gases, that is dry air, wet air and fuel vapor, or all these component gases are or behave like ideal gases, and then using Dalton's law of partial pressure, we can write this equal to Pa plus Pm plus P F, right. So, this is here I am writing A is dry air, M is moist air, that is wet air, and F stands for fuel vapor. So, these subscripts are used to denote pressure of the dry air, pressure of the moist air, pressure of the fuel vapor that is present in the mixture, and we could write these expressions using Dalton's law of partial pressure. Now, if we consider N and M, N is the number of mole. So, this is number of moles and M is the molar masses of each of these constituents, molar masses of each of these components, right. Then we can write this equation Pi. So, we can write Pi, that is inlet pressure, equal to Na plus Nm plus Nf divided by V into R A into T, where T is absolute temperature, this Ra is the universal gas constant. So, this is universal gas constant, T is absolute temperature, and M already we have defined. So, we can write one step further, that equal to Na by V 1 plus Nm divided by Na plus Nf by Na into universal gas constant into T. Okay. So, now what we can write, this Nm by Nmf, Nf by Na. So, this term you can understand easily that this equal to Nf by Na, that equal to we can write Mf by Ma into capital Ma by capital Mf. So, Mf by Ma, that is essentially we have used fuel air ratio F in the beginning. So, this is number of mole and M is the molar masses. So, then we can write F into Ma by Mf, and finally, we can write Nm by Na, that is the second term. So, if I write this term, so this is, and this can be written equal to M by Ma into Ma by Mm. So, this is M, and so this will be 1.6 into G, that you can assume, where G is the specific humidity of air. So, here G is the specific humidity of air. Okay. So, substitute, if we substitute all these quantities over here, then we can finally write Pi equal to 1 plus 1.6 G, where G is the specific humidity of air, plus F, that is fuel air ratio, into Ma, that is molar mass of dry air divided by molar mass of the fuel vapor. So, this is the expression that we can have. Now, here this is the pressure, and density rho I of the inlet air equal to Pi divided by R universal gas constant by Ti, right. So, having established the expression of inlet air, that is mixture of dry air, moist air and fuel vapor, we can write density of inlet air mixture is Pi divided by universal gas constant into Ti. Okay. So, what we can do here, from this expression we can easily calculate rho I2 divided by rho I1 can be easily determined, right. So, now question is, when the effect of atmosphere, we are trying to investigate the effect of ambient conditions. We assume that speed and fuel air ratio, these two quantities do not change. So, let me tell you one thing, essentially through this exercise we are trying to investigate the effect of ambient conditions on the performance, assuming that the fuel air ratio F and engine speed, these two quantities do not change. Okay. So, if we try to recall expression or equation 2, so try to go back to equation 2, where we could write the relation of indicated mean effective pressure at two different states in terms of density of the air and other two things, that is volumetric efficiency and indicated thermal efficiency. Try to understand F2 and F1, these two are basically fuel air ratio, but as I said, we are not going to change fuel air ratio and also we are not going to change the speed. So, if we use this expression to have the expression at this case, expression for this case rather. So, that means if we shall use equation 2 that I had shown, and we assume that engine speed and fuel air ratio do not change. So, if that is the case, then we can rewrite equation 2 in the reduced form, and we can write indicated mean effective pressure at 2 divided by indicated mean effective pressure at 1. So, F will not, so let us go back to that expression once again, that will help us to, F will not change, then indicated, if the speed is not going to be changed, then indicated thermal will be same. So, fuel air ratio is not changing, speed is not changing, then indicated thermal efficiency will not change. So, if we write this, then we can rewrite this expression for this particular case, and it will be rho 2 into eta volumetric 2 divided by rho 1 into eta volumetric 1, and that is equal to Ri. So, this equation is again 6. Okay. So, what we know that rho 1 and rho 2, this is proportional to P by Ti, right. So, rho I equal to Pi divided by R, that is universal gas constant, by T. That means rho I is proportional to Pi by Ti then. So, this is Ti. So, maybe I had written Ti here. Okay. So, this is Pi by Ti, and volumetric efficiency. So, we know volumetric efficiency is essentially actual mass flow rate, of air. This is defined as the ratio of actual mass flow rate of air to the theoretically calculated mass flow rate of air. Or volume flow rate. So, it is not mass flow rate, it is also volume flow rate. So, you also can write volume flow rate. So, this is also you can write volume flow rate. If you multiply with rho, then you will be getting mass flow rate, otherwise volume flow rate. So, then let us recall. So, if we go to the slide, so then eta just here only we can write here the final expression that we can write. So, you can understand that this quantity, so theoretically calculated volume or flow rate of air is same, that is stroke volume which is fixed. So, it is proportional to actual volume flow rate of air, which in turn depend on that is 1 upon root pi rho I. So, essentially eta v, this eta v is proportional to root Ti, because eta v is actual mass flow rate. So, actual mass flow rate means we know the velocity, that is 2 root delta p by rho, the rho I will be there. So, the rho I is essentially pi by r Ti. So, we will be getting Ti over here. So, this is proportional to Ti. So, if it is case, then this quantity rho 2 into eta, so it would be proportional to pi by root Ti, because rho is proportional to 1 upon Ti, eta v is proportional to root Ti, then from here we can write rho into eta v, it should be proportional to pi upon root Ti. So, then we can write, I mean this 6 expression can be written further here, that IMEP 2 divided by IMEP 1 is nothing but rho 2 into eta v2 divided by rho 1 into eta v1, that is nothing but p2 by p1 under root t1 by t2, and again this is Ri, because essentially I mean effective pressure at 2 divided by I mean effective pressure 1, which is Ri, and this equation in number is 7. So, what we did essentially, we have tried to estimate this quantity, that is ratio of indicated mean effective pressure at 2 different states in terms of pressure and temperature, which will vary if the ambient condition changes. And as I mentioned here, that this volumetric efficiency is essentially actual volume flow rate of air, which in turn depend on the velocity of air at the orifice meter that we have discussed, that is 2 root del p by rho. So, that rho is essentially pi by r Ti. So, this Ti will go off and this eta v is proportional to Ti. So, rho into eta v is pi by root Ti, and from there we could write the final expression of this quantity, which can be used to again predict the performance under different or for different operating conditions. So, if you would like to summarize our today's discussion, we can say that we have discussed about a technique or method to obtain some expressions analytically, and those expressions are useful to predict the performance of a particular engine under different operating conditions. So, we shall try to solve 2 different problems essentially to illustrate the concept that we have discussed in today's class, and that part we will do in the next class. Thank you very much.